Ciao Gianni.
Ciao.
Aspettiamo un attimo magari che arrivino anche Giulia e Riccardo. Intanto vi do il foglio delle firme. Puoi mettere anche la data in alto, per favore. Non si vede nessuno. Non vi ha fatto sapere nulla, Riccardo? Dai. Vabbè, iniziamo e poi se arrivano bene. Okay, hi everybody. So today is our last day, and our goal for today is to put together everything that we have seen so far. So the first part of the course, which was on reactive control using task space inverse dynamics for tracking reference trajectories, and putting that together with the second part, which was on trajectory optimization using the linear inverted pendulum model for generating a reference center of mass trajectory for a bipedal walking robot. And finally, also a second easier trajectory generation part for generating trajectories for the feet. So let's quickly review what we have seen last time. Well, we have started from motivating the need for something more than reactive control, which comes from the fact that reactive control is good for tracking reference trajectories if we have one already, which we know to be feasible. But it's very bad at anticipating future constraint violations because it has no notion of future state. And so we need to introduce trajectory optimization, which has a preview horizon, and so can take into account the fact that the actions that we take right now will have on our capability of not violating the constraints into the future. The downside of switching from reactive control to trajectory optimization is that since you need to predict the future behavior of the system, you end up with a problem which is always an optimization problem, but it has much higher dimensions. So we can expect it to be also slower to solve. So a possible solution to this problem is to use trajectory optimization in an offline phase for planning a reference trajectory. And then we can use TSID, which is a reactive controller method for tracking this reference trajectory. So use TSID, which is fast online, and trajectory optimization, which is slow offline. And we get the best of both. Another problem is that trajectory optimization when we have contacts is very hard because if you model contacts as infinitely rigid, you end up with a hybrid dynamical system, which is non-differentiable. So you cannot really formulate that as a standard numerical optimization problem and hope the solver to find a solution, because the solver is going to fail. Or second option, you can use like a softened version of the contact constraints, but to make it physically realistic, you need the stiffness of these contacts to be very high, which leads to a stiff differential equation, which is very slow to numerically integrate if you want to get an accurate result. So the solution to which our community of legged robots has converged is to use rigid contacts, but fixing the sequence of contacts. So we predefine in advance what is the gait basically of the robot, which for bipeds is trivial, just left, right, left, right, left, right. If you want, you could include a double support phase. So you have 4 different phases and you cycle between these 4 phases. And if you want to make things even simpler, you can also fix the duration in time of each phase, which is, by the way, what we did when implementing the optimal control problem last time. You could make instead time a decision variable of the problem by saying that these durations T1, T2, T3, and T4 are optimization variables of the problem. That is doable. And the problem remains smooth and differentiable. It becomes harder to solve for the solver, so it typically takes more iteration, but it's still something that is smooth. So quite good. Yet another problem we would have, even by fixing contacts, is that the model of a humanoid or a legged robot is high dimensional, because you have one position and one velocity for every joint of the robot, plus another 6 for the velocity of the base and 7 for the pose of the base. So you end up typically with a very large state space, maybe dimension 60 to 100 for each time step. And you have to multiply that times the number of time steps. So you end up with a very large problem. So if you want to solve this problem fast, you can try to use a simplified model which capture the main component of the dynamics you're interested in. And for walking robots, the number one choice is the linear inverted pendulum, which is super nice because not only it's a small dimension, but it's also linear. So it's the best you can hope for. And we are very lucky because despite its simplicity, it works very well in practice. So the linear inverted pendulum model, we saw that we can derive it by starting from the Newton-Euler equations for a single rigid body. And then we can take these assumptions. So assuming that we are making contact only with the feet, only with a flat ground, using a constant angular momentum and a constant height of the center of mass. And all these assumptions are rather close to reality if we are walking on a flat surface. Then we can derive from the previous Newton-Euler equations the following expression, which describes the relationship between the center of mass position, the center of mass acceleration, and the center of pressure, which is the weighted average of the contact points using the normal force as a weight. So since this weight, the normal forces can only be positive because you cannot have a force that pulls on the ground, you end up with this constraint that the center of pressure must be within the convex hull of the contact points. So if you are on a single support phase, so you have only one foot on the ground, and this foot is rectangular, as it is the case for many humanoid robots, then this constraint can be written simply as maintaining the center of pressure inside this rectangular shape of your foot. If you have both feet on the ground, such as in this scenario here, then the convex hull of the contact point is going to be slightly more complex, but it's still a polygon. So you just have a bunch of linear inequality constraints. Okay. So by the way, in our example, we have that the x-axis points forward and the y-axis points laterally. I think it points to the left. So since also the feet are aligned with these two axes, basically the problem for the x direction and the y directions are completely independent of each other. And so we can solve two problems instead of just solving one for both axes. But if we had that the feet are not aligned with the axis, so you have feet that are, for instance, with that orientation, then you have a coupling between x and y. And so in that case, you would need to solve a single problem for both x and y together. Okay. So the reason why we can solve two problems, one for x, one for y, is because our feet are rectangular and they are aligned with the axis. Okay, this is just a rearrangement of the previous equation with an interpretation that you can think of the center of pressure, Z, pushing towards the center of mass. This is really the way you can interpret this expression. So it's an unstable system because every time the center of pressure is not exactly on the center of mass, you're going to have a non-zero acceleration. So you're not going to be at equilibrium. We can write these equations in the standard state form. So we have a state which contains both position and velocity. The control input is the center of pressure. And this is the dynamics of our system, which is a linear dynamics, as we can see, because nothing inside these two matrices here depend on the state or the control. So we have constant matrices A and B. If we discretize this continuous time dynamics and we write it in discrete time, we have an explicit solution for the metric exponential of this matrix AC, which is this matrix containing hyperbolic sines and cosines. You could also use a numerical evaluation of the metric exponential. It's just that if you have the explicit solution, it's a bit faster to compute. That's why we are using it. But if you didn't want to bother writing down the hyperbolic cosine and sines, and you have a function for computing the metric exponential, then you can use that function here to compute A. Anyway, A is constant, so we have just to compute it once. So we wouldn't notice the difference in terms of computation time by using the metric exponential. We could do the same also for B, just the expression is a bit more complicated. There is an integral inside. So I think for B, it's way easier to use the analytic expression. Okay, so now that we know the linear inverted pendulum model, we could use it for planning a center of mass trajectory. So we have reference trajectories for the center of pressure and the center of mass velocity. The one for the center of pressure is simply given by the central point of the planned footsteps. And in this case, we are assuming that the footsteps are manually planned. So we decide in advance where we want the robot to put its feet during the walking motion. And then we provide a reference velocity for the center of mass, which should be consistent with the footstep plan. Of course, if the footstep go in this direction, we cannot ask for a velocity that goes to the side. I mean, we could, but you cannot expect to get good results if you do that. And we ask the center of pressure to always be in the middle of the foot, because that's the most robust condition, because we have a large margin from the sides of the foot, and we don't want the center of pressure to reach the side of the foot, because that allows the foot to tip over. Whereas if the center of pressure is in the interior of the foot cannot tip over by definition. Okay, and then we write down this optimal control problem, where we are trying to track the reference center of mass velocity and the reference center of pressure positions, subject to the dynamics of the system, which is the linear inverted pendulum dynamics, discrete time, fixed initial conditions, bounds on the center of pressure. The center of pressure must always lie within the foot that is on the ground, so the support foot. And optionally, we can have also a terminal constraint, which we played with a lot last time by adding terminal constraints on the final velocity and also possibly on the final position to make sure that we end up in a stable configuration. Okay. So your main job is to basically decide which weights you want to use here for these two terms in the cost function, and to decide whether you want to have also terminal conditions, which I think are good if you're doing trajectory optimization, because you want always to end up in a state which is an equilibrium that you can stabilize. If you wanted also to optimize for the footstep positions, you could do that quite easily just by adding P, the sequence of the footsteps, as a decision variable to the problem, which is something that we can actually try to do later. So maybe we start by trying to play, to follow with TSID the reference center of mass that we already generated. But then we can come back to the problem of trajectory optimization, and we can add the footstep positions as an extra variable to the problem, so that they are automatically computed instead of being provided by us. So you add P among the decision variables, and here you just add a constraint to make sure that the footstep at this time and at the next time are not too far from each other, because of course your legs have only a certain size, so you cannot take a steps of 3 meters. So this is for ensuring steps are close. Okay, then we took a look at the implementation, but that's, I think we can skip. And we executed this. Then we briefly discussed how to connect this trajectory to TSID. We have two issues. One is that the trajectory we computed has a very large time step, whereas TSID has a very small time step. So we need to do some interpolation. And the second issue is we need reference trajectories for the feet of the robot. So the interpolation, it's very easy to do. We just take the discrete time dynamics of the linear inverted pendulum, and we use a smaller time step here, the one of TSID, and we compute basically all the trajectory interpolating from one state to the next. And we can also compute the acceleration, again, using the linear inverted pendulum dynamics in continuous time. For the feet, instead, we said that we could use polynomial and enforce that we have initial position and final positions corresponding to the desired starting point and end point of the foot, and also initial zero velocity and final zero velocity. And here I showed you an example with a third degree polynomial. We have 4 coefficients. We write down 4 equations corresponding to these four constraints, and then this is gonna end up being a linear system of equations with four constraints, four variables, so we can just solve it using a matrix inversion. Okay, so we already did this script here, LIPM to TSID, which was doing the interpolation and generating the reference trajectories for the feet. So the only thing that's left is to do the walking. Yeah, and we are done with the slides. So I think we can move to our Visual Studio Code. So if you executed the script LIPM to TSID, then you should see in the same folder a couple of NPZ files. These are data files saved in the NumPy format. Especially, you want to have this one, Romeo walking traj TSID, because that's the file that contains the reference trajectories for TSID. So that file, you should copy it from the LIPM folder into the reactive control TSID folder, which I have already done. But yeah, let me do that with you so you can see it. So we go in the LIPM folder and we do copy. You can do star.mpz. So you copy all the mpz file. // reactive control / TSID. Voila. Because then the TSID script is going to look for that file locally. And now we can open the script X for biped walking. So this script actually does nothing very special because it uses basically the same formulations that we already saw last time when doing bipedal balancing following a given center of mass trajectory. So the formulation of the problem is exactly the same. You have a task on the center of mass. You have contact constraints on the 2 feet. You have a task for following the foot trajectory. Minimization of the angular momentum, joint posture, joint velocity limits, joint torque limits. It's the usual stuff we already saw last time. The only difference is that this time we are tracking a center of mass trajectory and reference trajectories also for the feet, which are supposed to make the robot walk. Okay, but the TSID formulation is the same as usual. So the script actually starts by loading the data file. Then, well, it decides which QP solver it wants to use. Actually, I didn't mention this, but there are also a bunch of other QP solvers that have been added to TSID beside AQuadProg. AQuadProg was the first one, but now some people added ProxQP and OSQP. But I'm always using AQuadProg. Okay, and then, yeah, the main new part is this one, where we are reading the data from the data file for the COM position reference, velocity reference, acceleration reference, and the same for the right foot, the left foot, and the center of pressure. We also have a reference for the center of pressure, which I don't think it's strictly necessary. In theory, it should be enough to track the center of mass, but it doesn't hurt. And we also have this contact phase, which is probably a list defining the sequence of contacts. So basically, this one tells me when I should be in contact with my right foot, and when I should be in contact with my left foot, which is of course alternating. Okay, then the problem starts with actually a negative index for I. You will see when the time is printed, because before starting to track the reference COM trajectory, we need to move the robot so that the COM is on top of 1 foot, because that was our starting point when we did the trajectory generation part, if you remember. So in the beginning, you will see the robot moves its weight on 1 foot so that it can break the contact with the other foot, and then it starts tracking the reference trajectory. Okay. So in this preparation phase, we simply, you see it's the one when I is less than 0, we simply set the reference COM to the initial position with a 0 velocity and a 0 acceleration. So we simply try to reach that initial state and we stabilize the system there. And we do that for, I think, a couple of seconds. And then after, when I becomes 0, we print start to walk, and we remove the contact with the left foot, because the left foot is the first one that has to move to take a step forward. And then at every iteration of this loop, we always check whether the contact phase has changed. So if you have to switch from left to right foot or vice versa. And if that's the case, we add and remove the contacts that we need to. And that's it. Then here we simply set the reference for the center of mass and the feet. We formulate the problem. We solve it with a QP solver. We check whether the solution has been found. We also check whether the norm of the velocity is too large. Here I have a threshold, an arbitrary threshold of 40. If the velocity is greater than 40, then I stop everything, because I assume that the robot is falling down. And here I'm just logging stuff for doing plots later, so nothing really interesting. I'm printing stuff. Here I integrate the system dynamics, and I update the viewer, and that's it. Then at the end, I can replay the video to see the behavior better if I want to. Okay, so we can try to run the script. So I'm gonna move to the reactive control TSID folder, and I'm gonna run TSID x for bipeds walking.py. In the meantime, let me open my browser so I can see the robot in the viewer. Okay, so there it is, the robot. Okay. Okay, that should be a good point of view. Then press enter to start. I press enter. The robot moves the center of mass to the right. Then it moves to the left and it starts walking. So step with the right foot, step with the left foot. And this is the end. So it stopped on the left foot. The right foot is not in contact. So as you could see, the motion was not really played in real time. It was slower than real time because I think that Docker on my machine is quite slow. But maybe if we play the video, it should be real time. No, doesn't seem so.
That for some reason when you play the video game it goes slowly than the simulation, because my simulation went like in real time, but the video no.
Yeah, I can see it's slow. Okay, let me check how it is done. TSID bipeds dot. There is actually no time sleep here, so this should be played as fast as possible. But yeah, okay, I see. So the reason why it's very slow is that it contains too much data. So I think it would be better to add the data points only when we display in the main loop, so that we have less data points to display, and it should work better. So let me check also the configuration file, which is RomeoConf. So the time step for TSID is 2 milliseconds. And we are displaying things every 20 time steps. So every 40 milliseconds, we are updating the viewer. Okay, this seems reasonable. So hopefully if I rerun everything, well, now I'm gonna first show the plots, then we can rerun stuff. So this is a plot for the center of mass. We have the reference in red, and the real trajectory is in blue. We can see that in X and Y, we have a quite good tracking. Z is constant, and we can see that the scale is very small. So actually we are tracking well even Z. This is the center of mass velocity. Again, we have a good tracking. This is the center of mass acceleration. Even here, I think everything looks good. We can see that the acceleration that we have on Z is not really constant, because it's very hard to maintain it really constant. But this is not shown very much in the position trajectory, which remains pretty constant. So we have very small oscillations in the center of mass height, which are more visible through the acceleration, but in the position, they're almost invisible. And here we can see instead the center of pressure for both the left foot and the right foot, plotted against the limit, so the bounds of the feet. So the top plot is for the X direction, the frontal direction, and we can see indeed that the foot is not symmetric with respect to its zero frame, because the frame is located below the ankle, but you have much more foot in front of the ankle than behind the ankle. So here the limits are not symmetric. In the lateral direction, instead, they are symmetric. And we can see that the center of pressure remains almost all the time very close to zero, so right below the ankle. And that's actually the best position. So it's not in the middle in this case. It's a bit more behind the middle point, but this is the best configuration for minimizing the torque that you have to apply at the ankle of your robot. So in this way, you're using very little torque at the motor, at the ankle motor. So this is a very classic choice for humanoids. In this case, I didn't plot the reference for the center of pressure, but only the real trajectories. Anyway, also the reference is going to be very close to zero, so I expect they should match quite well. Okay, so let me try to rerun this. Hopefully this time when we play the video, we should see something a bit more real time. Are you all able to run this? Okay, play video. Yeah, okay. Now it's faster than real time. I think it's better than having it slower. We can see better the kind of motion we're generating. We could also make it really real time. And we just need to introduce a sleep. So hopefully this takes very little time. So we could use this time sleep of conf dot display and times conf dot dt. This should roughly give you a real time visualization. If you wanted it to be really real time, you should measure the time it takes for the display method and subtract it from the sleep time. Okay. So let's go to the configuration file and look better at what kind of problem we are solving. Because I think we are probably solving a slightly simplified version of the problem. For instance, we are not actually considering torque bounds at the moment because we can see that the weight of the torque bounds is 0. Neither we are considering joint bounds. So one thing we can try to do is to add the joint torque limits and the joint velocity limits by making these weights 1 and see whether the robot is still able to walk. Maybe let me just run this. Okay. Let's see the video now, hopefully real time. Yeah, that seems about right. Okay, so even with the torque limits and the joint velocity limits, we can still execute that trajectory. But now to make things a bit more interesting, we can try to take steps that are a bit longer or faster. Because right now, I mean, the steps are very close to each other. So how do we do that? Well, we need to go back to this script LIPM OCP, the one that generated the reference UM trajectory. And we can try to play with the parameters. So the parameters for this script are defined all in the file RomeoConf, which is the same one we were looking at before. They are just slightly above, I think. Yeah, here we have step length, step height. So step height is just how much the feet are gonna be raised, are gonna rise. Yeah, rise, got it right. When they're moving from one footstep to the next. So just 5 centimeters. It's not very important, but the step length, that's important. And yeah, 5 centimeter is a bit small. We can try maybe with 10. 6 steps, also that doesn't feel right. Let's make it 8. We have a slightly longer walk. And apart from that, I think I wouldn't change anything. Then maybe later we come back here and we try to make also the step faster. Because now for each step, for each footstep, it takes 1.2 seconds, which is a bit slow. I think we can probably make it 1 and try maybe even lower than that. So every time you change these parameters, you need to basically do the whole pipeline. Go back to the LIPM folder, run the LIPM OCP script. You take a look at the trajectory you got, position, velocity, it seems okay. You end with a 0 velocity, which is good. That's a lateral instead motion, is good as well. Okay, after that, we need to run the LIPM to TSID script, which generates a new data file. So these are the new trajectories for the feet and for the center of mass. Then we need to copy the data file in the reactive controller TSID folder. And then we need to go, or maybe we could just run the script from here. So Python 3 / reactive control TSID x4. Okay, let's see. Let's see if it works. Don't have too high expectation it's gonna work, but let's give it a try. Seems to be working. Okay, let's see the video. We have 1, 2, 3, 4, 5, 6, 7. Not sure what's happened at the end, but until the end, everything was fine. So I would say that this walking is feasible. So it seems that the tracking of the center of mass was very good until the end. Velocity of the center of mass was basically 0 at the end. Also, the acceleration was 0, so it seems that we were in a good state for being stable at equilibrium. I don't know what happens there. Probably something went wrong with the contacts. That's my guess. Well, we'll figure it out. Let's try to play a bit with the time. So instead of 1.2, let's try to make it 1 so that it's faster. And let's see if it works. So LIPM OCP. Okay, so we can see now that the reference velocity we're giving is exactly 10 centimeters per second, because we are asking to take steps of 10 centimeters with a speed, with a time for each step of 1 second. So it makes sense that the reference velocity is that. Then we generate the trajectories for TSID. We could disable the plots so that we don't have to close those windows every time. It's faster. Where are the plots? You just need to comment the final line plt.show and the plots are not going to show up. Copy the npz file and then you run the script. Okay, same problem as before, but not regarding the walking. So the walking seems to be fine even with this faster pace. So what can we try right now? Any idea? In the meantime, I'm checking to figure out if I understand why it's falling down after everything is finished. Let me try to enforce that we end up with 0 references for all the tasks. So maybe we have a reference at the last time step, which is non-zero. And so after the motion has finished, it keeps trying to follow this reference, which is non-zero. That could be an option. And so I tried to add these 3 lines to enforce that the final reference is 0. But I'm not convinced that's the reason. Seems more like a problem of contacts. So before, when we were taking 6 steps, it wasn't there. It appeared when we switched from 6 to 8 steps. That's why I think it's related more to the contact phase and other stuff. Yeah. So what I didn't solve it. Which means I can remove this. In theory, should maintain the same contact phase at the end, because it shouldn't enter here to change the contact phase. I want to check whether my theory that this happens when we finish the trajectory is correct. Minus n. So we should start seeing problems as soon as we start seeing these prints. So we can try to make the steps a bit longer. Did you try already?
15.
15, it works?
At the end, it all.
Okay, but it does all the walking.
No. 6 steps. Yeah, exactly. 6 steps and then full.
6, but you asked for 8.
Yes.
Because it seems it's doing 6, but it's actually doing 8. Because it counts the first footstep as 1 step.
But right now it's losing balance at the system.
No, non so, l'ultimo passo c'è il piede, quindi va indietro. Scivola indietro, si trova all'origine.
Yeah, but there you're basically after the reference trajectory has finished. So it's not something related to the reference motion, it's something related to what it does after. It's just that I've tried to make the system be stabilized after the reference motion has finished to simulate what would happen on a real system. We could simply stop the simulation there and we wouldn't see that problem. So you could simply cheat and say you have a parameter here, which is called T-post, simulation time after walking. So if you set this to 0, you're not going to see that part and everything should be fine, which we could do just as a sanity check that the problem comes from that phase. But at this point, I'm pretty sure it comes from that phase. And since I'm there, I could also try to make the steps a bit longer, like 15 centimeters. So LIPM OCP. LIPM to TSID. Copy the MPZ file. And then I run the script. See, no more problem because I simply stopped the simulation after the end of the reference. So as long as we are tracking the reference trajectory, everything is fine. The problem arises afterwards, but it's not clear to me why, because this should be a stabilizable final configuration for the robot. Okay, here there was a problem with the sizes of things. Okay, this can happen when you generate the time, not making sure it has the correct shape. That's a detail. I just wanted to check this contact phase array. You see just an array containing right, right, left, left, right, right, left, left. Ah, okay, here it is the problem. You see, I found it. So the problem is that the contact phase list, for some reason, while it should finish with left, and you see that the weight of the robot is all on the left foot, it ends with a right. Okay, this is a very subtle bug. So what happens is that when you finish following the reference trajectory, the robot tries basically to put all its weight on the right foot, but the center of mass is on the left foot. So that's why it slips and it falls down. So the contact phase is generated either in the LIPM script or more probably in the LIPM to TSID script. It's this one here, contact phase. It's generated by this interpolate LIPM trudge, which is this method here. Which generates a trajectory which has a size of n control plus 1, the same as the center of mass trajectory and the center of pressure. And this remain is equal to not clear. So if contact phase of I minus 1 times n inner equal right, then you make this equal to left. Okay. Okay, yeah, it's a bit convoluted, but I think I get it. So basically this makes sure that for n inner time steps you have right, then for another n inner time steps you have left, and so on and so forth, which makes kind of sense, but you should make sure that does not apply at the end.
I think that the issue is that you are initializing one more element at the end, which is not checked by that is and has if statement. You're initializing always to right. So you should make sure that the last element is equal to the before last element. If you add,
Yeah.
you ensure that the continuity of the last element with the previous ones.
I think this should go here. So contact phase of -1 equal contact phase of -2. So the last one should be equal to the before last one. We can try if this solves the problem. So I run again LIPM to TSID. I copy the files and then I run again the script. Wait a sec, I should reintroduce the final phase with dpost equal to 1.5, otherwise I'm not gonna see anything. So actually this one, which for us looks like the first footstep, it actually counts as the third one, or how the program counts them. No, it seems that what we did didn't work.
Like we're not setting the correct reference for the right foot when the trajectory ends. it goes to 0. I mean, in my case, when we finish, the right foot goes
Goes
toward the
backwards.
zeros. Maybe we initialize everything to 0 and we can copy the last reference in the all remaining steps.
Yeah, it's possible. It's weird, it only showed up now, whereas when we were doing 6 steps, this was not a problem. So the reference for the right foot should be this one. With index -1, so we take the very last one. Yeah, there's a problem there. You can see that the very last one is at 1 centimeter in the x direction, whereas the one before is at 76 centimeter in the x direction. So here there was a problem. Which probably we could easily fix just by adding a -1 there. So we don't set the reference at the very last. We stop one before. Here I added a -1. Instead of I less than n, I added I less than n minus 1, line 140. Not sure it's gonna work because I've already tried a few times and I failed, so you can wait and see if it works before you change that. Yeah, it worked. So yeah, there were 2 problems, I think. I think they were both necessary to fix this. The contact phase and the reference for the last time step of the fit. So this was just a quick fix, which was not super clean. The clean fix would be to be done in the LIPM2TSID, which is where we generate the reference trajectories. But I think that, well, for now, this works. So I would actually like to reach the point where we break this to show you that it has some limits. So let me try to make this even longer. So 20 centimeter steps. Were you able already to make it break?
The time
Decreasing
decreases the time per step.
to how much? Okay.
Let's say you.
Okay, well, 20 centimeters should be a quite long step for this robot. Let's see if it's able to do it. Yeah, it was able to do it. The final pose is not beautiful, but okay, let's keep going then. Let's try to make it faster. Say 0.8.
I can do it in 0.7 seconds and 0.5 centimeter.
Okay.
25 centimeter.
So you can do 0.7 with 0.25.
Yeah.
Then let's go 0.30. Oh wait, I have to regenerate. I think I didn't regenerate last time, so it didn't really count. Okay, I think this is really too much, so it's gonna break. Didn't work. Yeah.
Solo un 0.7, senti 0.6 non senti di nuovo. Però un 0.6, 0.2 non riesce a camminare.
I mean, here the problem is that it doesn't manage to walk, is that the script doesn't work. The LIPM to TSID script has a problem with the dimensions. Yeah, it's not very robust, that script. Ok.
Se vuoi, per romperlo 0,6 secondi e 35 centimetri. E iniziava a fare cose strane.
Ok.
0 secondi 20 centimetri si rompe comunque. Immagino con 35. Sarà divertente.
Okay, I think I've tried something a bit more reasonable. Let's see if it works. Oh, that's a long step for this robot. Yeah, it's not going well. Yeah. It did a few steps, but you're not gonna see the end of this. I don't know why it's not stopping the simulation, because I thought it would stop when the velocity was greater than a certain value. Yeah, but okay, that was 40. Now we're only at 21. So it's not enough to make it stop. I think I could reduce that to 10. It will be a more reasonable limit. So for me, with 0.8 seconds and 30 centimeters, it failed. For you, it works with the same parameters?
Maybe I can change something that you changed.
Did you introduce the torque limits and the joint limits? Yeah, that helps. Here, W torque bounds, W joint bounds. Yeah, so probably we can double check if I remove the limits and run this again, probably it works. Yeah, that shows you the importance of considering those limits. And now I removed the limits, I played again. So it should probably work if it worked for you. So this shows you basically what you could do if your robot was stronger. Removing the torque limits basically means making the robot stronger. Oh, there was still a final movement there, which was not super nice, but it survived. Show it to you. Did you see that? Are you getting the same movement as me there? Okay, but this is not feasible if we consider the torque limits and the velocity limits. So it's not something that you can really play on that robot. Okay. So at this point, I think what we could do, unless you have better ideas, is to go back to the LIPM script. This one, LIPM OCP, that one generates the center of mass reference trajectory and try to introduce the optimization of the footsteps as an additional feature. So that instead of pre-planning the footsteps, we only give a reference direction and a reference velocity. And the footsteps are automatically planned by the solver for us, which I think is pretty cool. But before we do that, I think we could take a break because we've been going for more than 1 hour. Okay, so let's take 10 minutes. Julia, can you show up so I can verify that you're there?
Hello.
Ciao.
Ciao.
Riccardo invece non si vede, desaparecido. Ok, va bene. Ok, ci vediamo tra 10 minuti.
il trucco adesso che non è niente da fare, no?
Non so, però.
Lo so.
So we have an ongoing discussion with the people here. I'm talking to you guys at home for what we could do in the remaining time. And one option was what I was mentioning before the break, which is to add the automatic footstep planning in the trajectory optimization problem here, which seems, I think it's feasible in 1 hour to do it. So we should be able to see the results of that. Another option instead could be to leave the trajectory optimization problem as it is right now, but instead of executing it only once at the beginning, we could execute it here inside the control loop so that we replan the center of mass trajectory every couple of milliseconds. We should make us a bit more robust, especially if we introduce perturbations such as pushes. And I mean, ideally, we could do both. We could do first the automatic footstep planning, and then we could integrate that inside the control loop. That would be the best, because so basically what you would get is that you start maybe the robot asking it to walk forwards, and then if you push the robot to the side, it moves the footsteps in order to avoid the fall. So if you push it to the left, it's gonna take a few steps to the left, and then it's gonna go forward again. Which is very cool. So we could either focus on the trajectory optimization part, adding the footstep planning, or we could focus on the MPC part, calling the trajectory optimization problem from inside the control loop. We cannot do both, that's too ambitious. So we can decide which one you want to try to do right now. Anybody has a strong opinion on what to do? Strong preference?
I would rather MPC.
Okay, MPC. Anybody else? Gianni Lunardi said footstep planning, so we have one against one. You're with Gianni? You too? Okay, so Matteo, you probably lost. Unless Luca and Giulia, remote Giulia, vote for MPC.
I stay with the majority.
Very democratic. Okay. Footstep planning. Okay, let's do the footstep planning. So I think we can probably implement everything inside I don't know. No, let's make a copy of this just to be sure we don't mess it up too much. So we can take the LIPM OCP file and do save as, and then we call it LIPM footstep OCP, something like that. Just give it a different name. I also changed the name of the class. And okay, so right now we have something that's completely equivalent to what we had before. Lines here, we can remove them because they do nothing. We have a cleaner script. Okay. So what we want to do is to add some optimization variables for representing the position of the footsteps. just as a reminder. Basically, the footsteps would take now the same role that uref is taking at this moment. Okay. So we need to introduce some extra variables, but we don't want one variable for every time step, because we don't want to change the footstep position at every time step. We want to change it every few time steps. So we need to remove from the input the reference COP trajectory, uref, but we need to add another variable, which we can call n step. And we can add a comment, n step, number of time steps per footstep. Which I think it's a variable that we should already have here. Yeah, which we called number dt per step, which maybe is a better name. So we could use this name. Okay, so to decide how many variables we should have to represent the footsteps, we should take the total length of the horizon, which is n, and we should divide it times the number of dt per step. Make sense?
No, sorry.
So if we have an horizon of 20 time steps, so capital N is equal to 20, and this variable number dt per step is 6. So we know we are going to have one footstep for 6 dt, then another footstep for another 6, and we get to 12, another footstep for another 6, and we get to 18. And then we need to round this to the next integer, because we need yet another footstep for the last 2 time steps to get to 20. So I think that the number of footsteps we need to plan is given by the ratio between n and this variable, but we need to approximate this ratio to the next integer. Because in general, it's not going to be an integer value if we just take one divided by the other. So we could do like NP. No, NP is not a good name. And footsteps equal numpy.ceil. So ceil is a function that takes the next integer, starting from a double value. And we should divide n divided by the number of dt per step. Okay. So this tells us how many footsteps we need to take. So that now that we know that, we can create the variable. So self.opti.variable and footsteps. Compute how many footsteps we have in the horizon n. Okay. So now we have this extra variable. We just need to be careful because we don't have as many of these variables as we have of the other variables. So when using this variable, the time index is not going to be the same as for the other variables. Okay, because we have less of these than of the others. So what we need to do is to replace uref in the cost and in the constraints that we already have with P. But when doing so, we should also change the time index that we are using, because it's no longer going to be I, but it's going to be I divided by this variable here. Makes sense? So if we know that we are on the same footstep for 8 time steps, then we know that from time step 0 to 7, we should always refer to P0. So if we take the time index I and we divide it by 8, then we know that as long as I is from 0 to 7, when we divide it by 8, we get 0. I'm talking about an integer division. And then as soon as we reach time step 8, then we do 8 divided by 8, so we get 1, which means that we switch to the next footstep. Make sense? Okay, so here we should use I divided by n footsteps. However, probably Python's not gonna like this.
It's double slash.
Oh, really?
No, that is the remainder.
Let me try. So if we do 7 divided by 8, you see it gives me. No, you're right. Seems to work. Okay, let's try with a double slash. So that should give us the integer division. And then also here, when we have the inequality constraints on the COP, instead of uref, we need P. And again, here instead of I is I divided by n footsteps. With the double slash. Same thing here for the terminal constraint. And here we want to reach for the last footstep position, but we know that the length of the footstep is n footsteps. So we simply do n footsteps minus 1. Okay. So this is not the complete problem, but I think we could give a try to this problem to see if we did everything right before modifying it even more. So what we are currently missing are the kinematic limits, which make sure that 2 consecutive footsteps are not too far from each other. But we can try to see whether this works already. So moving to the main script, now in theory, we should be able to remove a lot of what's been going on there. For instance, we can remove the manual footstep placement. and the uref trajectory because we no longer need it. And instead of passing the uref, we should simply pass this variable number dt per step. We should also update a bit the way we do the plots because now we no longer have the uref trajectory. So we should recover the footstep planned by the OCP, which then is going to be a bit of a nightmare to plot, but we can deal with that. So we should do something like this, like px, and we recover the variable p, and we do the same for the y direction, py, from the solution of the problem for the y direction. And so here we plot px, and here we plot py. Knowing that this is not going to give us the result we expect, because these trajectories for the footstep don't have the same length of the others. So they are plotted basically on a different time scale. So ideally, before plotting them, we should modify and also the saving of the data. We should remove these two lines because at the moment we don't have the correct information. We can take care of how to save the data later. Let's just maybe fix the plots first. I'm thinking of an idea. So maybe we could do something like that. We create an NumPy array. Well, actually, we don't need it. We can create just a list. So we put together the OCP.py divided by the number of dt per step for I in range n. That should basically replicate the same value for a bunch of times, so that this trajectory now has the same length as the others. This is just a fancy way that Python gives you to do a for loop in one line. I think you should understand the notation, right? And we do the same for the other. So hopefully this works. Now that I think about it, I think here we made a mistake. Here we should not divide by the number of footsteps, but we should always divide by the number of dt per step. Here it was correct number of footsteps, because we want to access the last one. But in the other place, when we do the division, it's always divide by number of dt per step. Okay, let's try if this works. So Python 3 LIPM footstep OCP.py. Let's run it with a -i so that we remain inside the interpreter after running. Okay, we got an error. Wrong number or type of arguments for function opti variable. Okay, so it's complaining here where I'm creating the variable p. So probably this doesn't give an integer. So let me try to add int in front so that I convert this to an integer. Okay. Now it seems it's working. At least it's working for the x direction, which is already something. So you can see that this, the dotted line, which you can see is almost superimposed to the center of pressure, represents the automatically planned footstep trajectory. Which is, by the way, I think pretty similar to the one that we were providing before, which makes sense. So for the x direction, it seems that we are already in a decent shape like that. I mean, we should add some extra bounds in theory, because, I mean, for how it is done, this problem has no boundaries on how far apart two footsteps can be. So if we ask the robot to move at 10 meters per second, it's probably gonna make the footstep 10 meters apart from each other, which is not a good idea. So we should add some limits there. But I think that as long as we ask for reasonable reference velocities, this is gonna give us reasonable results, even without those extra limits. Okay. So that's for the x direction. For the y direction, things are a bit more complicated, because we should take into account that the robot is not like walking, putting its feet one in front of the other. Actually, most robots cannot do that. Kinematically, they don't have the range of motion to do that. But that is basically what is happening here, because you can see that the footsteps are all one in front of each other. We have a constant value for the footsteps. And well, if you think about it, it doesn't make much sense to automatically plan the footsteps in the y direction in this context, because we're just asking the robot to move forward. So in the lateral direction, we know that we're going to simply maintain the 2 feet at the same position as they started. So in this case, since everything is coinciding, basically the solver is putting the footstep, the center of pressure, and the center of mass position at the same value, then the velocity remains 0, because this is an equilibrium for the system. When center of pressure and center of mass are equal, acceleration is 0, and so the velocity remains constant at 0. But this is not, we know it's not really feasible, because we need to make the center of pressure move from left to right, and we need to have this sinusoidal motion. So if we want to make this work also for the lateral direction, we need to add something that tells the solver that we need to have this alternation of left and right. Any idea how to do it?
Step the y coordinate is set for the value.
Well, if we set the y coordinate of P, basically it means we go back to what we had before, where the position of P was already manually defined by the user and passed to the solver. That was basically what we had in the previous file, which is an option. I think in this case, it's the most reasonable option. If you know already that you only want to move forward, doesn't make sense to optimize the lateral direction. You already know that you're going to go in a straight line, so you maintain the lateral footstep position constant. However, if we want to try to write something that could work also later for lateral movements, which could be also something we could try, we need to still optimize the footstep position even in the lateral direction, but we need to add some constraints to make sure that the trajectory that we plan is feasible. So imagine your robot has, so let's use black for the right foot and red for the left foot, so that we distinguish them. So let's imagine that we start here with the right foot, and we want to move in this direction. Where do you think would be a reasonable place to put your left foot? Can you put it here? No. Okay, you cannot put it there. So we can say that maybe we want to put the left foot on the left of this half plane. That could be already a good starting point. So we could add a constraint that the y coordinate of the left foot should be always smaller than the y coordinate of the right foot minus an offset. And we could do the other way around for the right foot. So we need to be greater than the y coordinate of the left foot plus an offset. So basically, the solver is forced to make the footsteps, one a bit more to the right, one a bit more to the left, and cannot put them too close to each other. That could be an option. Another option could be not to constrain the position of the foot with respect to the position of the previous footstep, but to the position of the center of mass. because you can imagine that if your center of mass is here, this is typically the way we represent the center of mass at the end of the current footstep, then maybe you could make your footstep, your left footstep there. But if instead your center of mass is there, maybe you cannot reach that footstep and you need to instead move it there. So it kind of makes sense to constrain the position of the foot with respect to the position of the center of mass, because those 2 points are related to each other. I mean, when you move your foot to the left, you're also moving the center of mass, because your leg has a weight, and that weight is changing the position of your center of mass. And these two things cannot be too far apart from each other. So I think it could make even more sense to add this constraint with respect to the position of the center of mass. I think that in robotics, most people put the constraint of left foot with respect to right foot and vice versa. But I think it makes even more sense to constrain with respect to the center of mass. Of course, we need to know whether the first footstep is the left one or the right one in order to make this work. Because the constraints we put on the left one are not the same that we put on the right one. They are basically the mirroring of the same constraints. We need to mirror, and we need to know on which side we are starting. So maybe one very simple thing we could do is to say that the left foot should be on the left of the center of mass, and the right foot should be on the right of the center of mass, plus and minus some offset. Okay. So we need to decide a reasonable offset, and we need to specify to the solver on which foot it is starting the motion, if it is starting on the right or on the left. So it starts adding the constraints on the right side.
Is it not always true that the left foot is on the left of the center of mass?
Yeah, but the solver at the moment has no notion of left and right.
Oh.
And the first footstep is actually starting exactly on the center of mass. So there is nothing that tells the solver if the next one should be on the left or on the right of the center of mass. So we need to provide that information. Okay, so actually at the moment, this is only necessary for the Y direction. This is not necessary for the X direction. So we could either make a copy of this solved method, but I think it's a bit of a pity because most of the code would be the same. So maybe we can more simply add a parameter as an input. Which is, I don't know, lateral which by default is equal to none. So when we call this method without specifying lateral, we do the planning for the forward motion. When we instead specify lateral, the lateral flag, we do the planning for the lateral motion, and so we add these extra constraints on the position of the footsteps. Okay. And we need to specify also what is the minimum offset that we want to add from the footstep to the center of mass when we take the step. Okay. And that could be another parameter like lateral footstep offset, which by default is equal to none. Okay, so we need to introduce this constraint, but we don't need to introduce it for every time step. We just need to introduce it for every footstep, which are less than the time steps. So what we can do is that we can add another for loop here, saying if lateral is not none for I in range n footsteps, self dot opti dot subject to, and then to add a bound we do this well, let's add first a simple bound, so we can simply write that the footstep position be I. Let's do it supposing we are planning for the right footsteps. So pi should be greater or equal to the position of the center of mass, which is x0, comma, and now we need the time step corresponding to I. So we need to do the inverse operation of what we were doing before. So before in these loops, I was the time step, and we wanted to recover the index of the footstep. So we were dividing by number dt per step. Now it's the opposite. We have I, which is the index for the footstep, and we want to recover the corresponding time step. So we need to multiply times this variable. So it's going to be I times number dt per step. So this is exactly the position of the center of mass, but we said that we want to add an offset. So we add lateral footstep offset to this. So this would be the constraint if this is a constraint for the right foot. And then we can write the constraint for the left foot, which is thus that pi should be less than or equal to the position of the center of mass minus the lateral footstep offset. Okay. And now we need to decide on which side we are. So we know that the footsteps are alternating left and right, left and right. So it should be quite easy to figure out which one we should do. We just need to basically look whether I is even or odd. So once we add it for the right, one for the left, one for the left, one for the left. And here we need to know actually the information of whether the first one is the right foot or the first one is the left foot. And we could assume, we could use actually this flag lateral to pass that information to the solver. So we could assume that lateral is a flag that is equal to right or left. So we could say if lateral equal right, then we say target equal to 0, else target equal to 1. And here, instead of comparing the rest of the division with 0, we compare it to target. So depending on whether we are starting on the right or on the left foot, we switch basically the order of the constraints that we add. Also, we cannot really add the constraint on the first footstep because we are assuming that we are starting with the first footstep that's exactly on top of the center of mass. So we don't want to satisfy these constraints for the first footstep. So instead of doing range of n footstep, we should do range 1, comma, n footstep. So we start with the index 1 instead of the index 0. Okay. So now next time we call solve for the y direction, we should specify lateral equal to right, because I think if I remember correctly, we were always starting with the right foot. And we should specify a value for this parameter. So let's give it a try. So here, say right, and we give a value for this parameter, which could be, I don't know, 10 centimeters. Just to try something out. Okay. Let's try. So the trajectory in the x direction shouldn't change, and indeed, I think we have the same as before. But now in the y direction, we have something completely different. So we can see that we have indeed these left and right movements. I think I didn't do the computation of the target right, because you can see that we start at minus 0.1, so then we should move at 0.1, because the robot basically starts at 0. So this trajectory should be more or less centered around 0, and instead it's on one side. So this should be easily fixed. I just need to set here target equal to 1 and here target equal to 0. And if I run it again, now it should work. Yeah. Okay, now you can see that the trajectory is more or less oscillating around 0, which is what we wanted. And we can see that indeed, at the moment where we create the next footstep, it is at least 10 centimeters from the center of mass to the side. And here also we have 10 centimeters to the side.
For me, C is not working. Can you show me back the code?
Did you start the for loop at 1?
Yes, no, I mean, I used to get the constant y in solution.
Did you specify the lateral flag when you called the method solve? Did you specify also the lateral footstep offset? Mm, no, I think I've changed only those extra constraints, and I've added these parameters when calling.
Okay, now it's working. I don't know.
Okay.
It was just a plus and a minus.
Okay. Okay. Actually, I just realized that we haven't added the constraint that the first footstep should be on the top on top of the center of mass, which is something that we actually assumed before. You could see it in the plot that they were not, I mean, they were very close, but they were not exactly aligned. So I think if we want to get consistent results with respect to what we were doing before, we should also do that. So we can add that extra constraint here, maybe. So self.opti.subject to, and we say that P0 is equal to X init. That the center of mass starts exactly on top of the footstep. Was starting pretty close, so probably we wouldn't have noticed, but just for being sure that we are never getting wrong results. Constraint shape mismatch. Yeah, okay, I think that X init contains two variables, both the position and the velocity, so I need to select only the first coordinate. Okay, so that is X, and I can check here, you can see that the footstep is exactly at 0 as the center of mass. And this is y. And even here now, I have that the footstep is exactly on top of the center of mass at time 0. So we have, now we have COM, trajectory generation, with automatic footstep planning. So now we can do one very cool thing.
Can you go back to the condition that you are?
It's P0 equal X init 0. So basically this means footstep at time 0 on top of COM at time 0.
Of the plot, why the left on the left foot, the center of mass is at like 0.8 instead of if you go back to the second.
Because we are starting on the right foot. So when we initialize the system, the robot is centered at 0, which means that the right foot is at minus something and the left foot is at plus something.
Yeah, but I was expecting that the robot was at plus 0.1. Instead, it's like at 0.9. The center of mass.
Oh, that's just in the configuration file.
No, but I mean, I was expecting to see that it goes between 0.1 and minus 0.1.
Okay, so the reason why it starts at 0.9 is because here we ask it to start at 0.9. So if we change this value, you're going to change the initial position of the center of mass and the footstep. So this is in the configuration file. And the reason why I chose exactly this value is because when we start the simulation with TSID, the robot is initialized with the right foot exactly at that coordinate.
Okay.
Okay. Then the reason why the oscillations are not exactly between minus 0.1 and plus 0.1 is because the constraint that we added is not of footstep with respect to footstep, but is footstep with respect to center of mass. So you should compare the position of the footstep with the position of the center of mass when the footstep is making contact with the ground. So basically, you should measure this distance here and this distance here. And if you do, you're going to see that they are 10 centimeters. Okay. We can try to make that bigger. So here, instead of 10, I could try to put 20 centimeters. And I could check what we get. Of course, X doesn't change. But now in the Y direction, everything is skewed basically on the positive side because we start at minus 0.1 roughly. And then when we take a footstep to the left, we need to go 20 centimeters left to the center of mass. So the first footstep is at 0.27. And then it becomes symmetric, but with respect to some value which is non-zero. But 0.1 was a better choice. So what I wanted to try, don't know how easy it is to do, but we could try to make the robot walk laterally instead of in the forward direction, which I think something a bit different from what we have done so far. And it should be quite easy because basically everything we are providing to the system is just the reference velocity. So now this reference velocity we are providing is this value here, the step length divided by the duration for one step. And now instead of providing a positive value for x and 0 for y, we could do the other way around. We could set to 0 the reference velocity for x and set to non-zero the reference velocity for y. And now we should see the robot that does the lateral walking. Okay, so this is just a mistake in the plot. I'm plotting in the x plot the reference velocity that now I'm giving to y. That's why here it's non-zero, but actually we are giving 0. So in the x direction, nothing happens because I'm asking for 0 velocity. So the robot is not moving at all in the x direction. And in the y direction instead, you can see that I get the typical pattern of lateral walking, which is not bad. So now if we want to try this on the complete system, we just need to fix the data saving part. Because before we were saving also the reference center of pressure trajectory, which now we no longer have, but this is nothing more than the footstep trajectories. So we just need to combine these two trajectory px and py to get urf. So that should be pretty simple. It's just urf equal np dot not sure if it's a vertical stack or a horizontal stack, but let's try with a vertical stack. So we just stack on top of each other px and py. And then I'm going to check whether that is the correct size. So that's pretty easy to fix. And then we need the footsteps. That I'm not sure which format it was before. So what I'm gonna do is that I'm gonna run the previous script and I'm gonna inspect the format of that variable. So footsteps. Okay. Okay, that seems to be basically what right now we have as the variable of the problem. So it should be pretty simple. So basically we should simply read this. Footsteps x equal no. footsteps y equal same thing. And then footsteps an underscore, want to keep the same notation. Footsteps is gonna be just a vertical stack. Yeah, you're right, it's horizontal. np dot h stack of footsteps x and footsteps y. So dimensions are never gonna match, but let's just run this and see where it fails, and then I'm gonna fix it. Yeah, I should recover the data before I solve the second problem, otherwise it complains. So I'm just gonna move these two things here. Here I just do the stacking. Okay, well, those are my references. Let me just print footsteps. Yeah, didn't work. I knew it. So if I print footstep X and footstep Y, okay, then probably I should do np dot horizontal stack of footsteps X dot transpose and footsteps Y dot transpose. This should not work again. Why? Okay, then I should do a vertical stack and then take the transpose. That gives me the correct shape. Don't ask me why. So vertical stack, and then you take the transpose of this. Let me check if uref has the correct size. What shape? 2 times 64. So I guess it should have the same shape as COP, no, COM statex. Let me check. COM statex dot shape. Yeah, they have the same shape, and COM state is transposed here. So probably I should also transpose this one here. Okay, so now I think they have the correct shape. So you need to use vstack and take the transpose in both cases. And now we need to rerun this so that we have the data file that contains the data in the correct format. And now we run the LIPM to TSID file. Incredible, it worked. And now we copy the MPZ file in the TSID folder, and we run the script. It works.
No, sta per cadere. Salva.
Yeah, those are long steps for this robot. Okay, maybe we have some trouble again with the terminal configuration, but apart from that, it seems to be working. So now it's playing real time. You can see how difficult it is for the robot to track this. So yeah, it was about to fall at the end, but so the tracking is pretty good until the end. But you can see how challenging this trajectory is from the center of pressure. If you remember before, when it was walking forward, the center of pressure was more or less always very close to zero. Right now, instead, especially in the lateral direction, you can see that it's really getting very close to the boundaries of the feet. So the robot is really struggling. It's using almost its full range of center of pressure in the lateral direction.
Do you see that the strain from the fact that the feet should be at least 10 centimeters apart from the center?
No, I didn't get the question, sorry.
The strain that we added so that the feet are not one are still active.
Yeah. Yeah, otherwise we would have the feet on top of each other in the lateral direction, so at least something like that. But-
Reducing the distance so that the robot can,
But
otherwise maybe the center of pressure has to swing when the foot approach the other. I don't know, maybe.
so the constraint that we added is just to prevent the 2 feet
Yeah,
from being one in front of the other, and that we can see. We could already see it with the LIPM that the feet, they were never on the same side of the center of mass. We had always 1 foot on the right and 1 foot on the left, so that is maintained. But what we see now here is not the footstep position, but it's the center of pressure. So assuming that 0 is the middle of the foot, you can see how much the center of pressure is moving from the middle of the foot. And the 2 lines here, the dotted red and green lines, are the boundaries of the foot. So we can see that the center of pressure is not maintained in the middle of the foot as it was before, but now it's going very close to the boundaries. Okay, I'm really impressed this worked because I never tried this before. So it rarely happens that things work the first time you try them. So we got lucky today. Okay. I think it's good to end with a success. So I would stop here. I wouldn't try anything else. Do you have any question? So maybe a couple of words on the evaluation. So I guess that you guys need an exam, some form of evaluation to get the credits of the good kind. And I haven't decided yet what exactly the exam is going to be, but the format of the exam that I've used on the last years, which I think I'm going to keep also for this year, is basically I'm going to provide you a list of small exercises with questions. And in order to answer, you will need to basically use the scripts we have played with. run some simulations and answer based on the results that you obtain. Okay. So of course, if you have some ideas that you would like to explore related to the tools we have used, and you'd rather do your own thing instead of doing the exercises that I'm gonna provide for everybody, I'm very open to listening to your request. So if we can make this something useful for your research, for your PhD topic, I would be very happy about that. Otherwise, just stay tuned, and I'm gonna let you have the list of questions that you have to answer. So you will then send me a report. I don't need anything extensive, just a few pages answering the question and maybe providing some plots to show me the data that you generated for answering the question. And then I'm gonna evaluate the report, and well, I don't think I need to give you a grade. It's just pass, no pass. So far, nobody has failed. So
we wrote to the secretary from Genova, and they asked us if you can provide the program for this year's course.
okay.
Because you sent us the program of 4 years ago.
Which is the same.
Yeah, but they want the one for this year.
Okay, I'm just gonna copy paste this.
Yeah, if you can just change the date.
Okay. I sent you the flyer.
Yes, the flyer. Yeah.
Yeah, but I don't have a flyer for this year. That's why I sent you the old one. And I did not generate that flyer. It was the secretary who generated it.
Yeah, I think it's worth it's just a piece of paper that it lists what we did here.
Okay. Okay, I'm gonna give you something.
A bullet point. I can also create it and find
Okay. No, but I can print the syllabus.
Yeah.
I have the syllabus, and I add a date and my signature, and then that's good, right?
Fine.
Okay.
Thank
Okay, Julia, Gianni, are you still there?
Yes.
Okay. Okay. Then I think that if you don't have any other question, we can stop here. And I'll let you know through Classroom the question for the exam. Okay. So, buon weekend.
you. Thank you.
Tanto. Ciao.
Grazie, buon weekend.